Marjeline Belvis from GE 101.
Noriza P. Calderon from GE 101.
Bianca Dorothy B. Brusas from GE 101.
Joshua Pimentel, GE 101.
Pauline May Alpay, GE 101.
Jazel Andrews, GE 101.
Zario, GE 101. Yeah.
Good day, classmates. Today, we are about to tackle and discuss
Basically, nuclear chemistry is the study of radioactivity and nuclear transmission. The objectives of this video is to let you know and understand why is a nucleus unstable, radioactivity and radiation, forms of nuclear reaction, radioactive decay and half-lives, and nuclear shielding. Here are Ms. Calderon and Ms. Bianca to give us an introduction.
To start with our topic, let me tell you that nuclear chemistry deals with the changes in the nucleus, and the nucleus is made up of protons and neutrons. When a nucleus is unstable, it causes radioactivity, and radioactivity produces radiation.
an atom with unstable nucleus is called a radioactive atom. It gives off radiation and forms a new nucleus. Thus, radiation gives off of gamma energy or alpha and beta particles. When an atom gives off radiation, it becomes more stable.
But first, why is a nucleus unstable?
A nucleus is unstable because it has too many protons and neutrons. Its stability is based on ratio of protons and neutrons, and because of the strong mysterious force that fails to hold the protons and neutrons together.
There are three types of nuclear radiation. First, the alpha particle decay or alpha radiation. Second, the beta radiation. And the last or the third one, the gamma radiation.
The alpha particle decay is when a nucleus has too many protons and neutrons and gives off some particles that is made up of 2 protons and 2 neutrons, which is a new nucleus formed.
For example, a neptunium with an atomic weight of 237 and atomic number of 93 undergoes alpha particle decay. An alpha particle has an atomic weight of 4 and an atomic number of 2. So, 93 minus 2 is equals to 91, and 237 minus 4 is equals to 233. And from our periodic table, an element with a 233 atomic weight and atomic number of 91 is equivalent to Pa, or the protactinium.
While a beta particle is when a nucleus has too many neutrons. So a neutron turns into a proton and then flies off as an electron.
For example, a carbon, which has an atomic weight of 14, an atomic number of 6, and a neutron number of 8, undergoes beta particle decay. A beta particle decay is when a neutron turns into a proton and flies off as an electron. So, the number of neutrons of 8 turns into 7, and the proton from 6 turns into 7 in the product side. So, an element with a number of protons of 7 and atomic weight of 14 is a nitrogen.
And for the gamma radiation, it is when a nucleus gives off energy, no mass, and also it has the same elements. It happens to make the nucleus more stable.
Alpha particles are least dangerous terms in external exposure. They don't penetrate very deeply into the skin. In fact, clothing can stop alpha particles. Unfortunately, it can be inhaled or indigested, usually in the form of radon gas. Once digested, alpha particles can be very dangerous. However, they don't typically cause radiation sickness. Instead, they can lead to lung cancer.
Beta particles are electrons that move quickly. They travel several feet when emitted, but they are blocked by most solid objects. This particle is about 8,000 times smaller than the alpha particle, and that's what makes them more dangerous. Its small size allows them to penetrate clothing and skin. External exposure can cause burns and tissue damage along with the symptoms of radiation sickness.
Gamma rays are the most dangerous form of radiation. These extremely high energy photons can travel through almost all forms of matter because they have no mass. If you are exposed to gamma rays, they pass through your entire body, affecting all your tissues from your skin to the marrow of your bones. This causes widespread systematic damage. Boom.
The process of emitting of particles of an unstable nucleus is called radioactive decay. Radioactive decay is a stochastic or random process at the level of single atoms, in that, according to quantum theory, it is impossible to predict when a particular atom will decay.
The chance that a given atom will decay never changes. That is, it does not matter how long the atom has existed. For a large collection of atoms, however, the decay rate for that collection can be calculated from their measured decay constants or half-lives.
This is the basis of radiometric dating. The half-life of radioactive atoms have no known limits for shortness or length of duration, and range over 55 orders of magnitude in time.
The radioactive half-life for a given radioisotope is a measure of the tendency of the nucleus to decay or disintegrate, and as such is based purely upon that probability. The tiny nuclear size compared to the atom and the enormities of the forces which act within it make it almost totally impervious to the outside world.
The half-life is independent of the physical state, solid, liquid, gas, temperature, pressure, the chemical compound in which the nucleus finds itself, and essentially any other outside influence.
So here are some problems regarding half-lives. The half-life of zinc-71 is 2.4 minutes. If one had 100 grams at the beginning, how many grams would be left after 7.2 minutes? Here's our formula for half-life, where A is the final amount, and here is our initial amount multiplied to 1/2, where 1/2 is a split factor, and time is indicated by capital T, and H is the half-life. So here's the solution. You can just direct substitute it into your calculator. Just let me show you this method. First, I get the half-lives where I divided the time to the half-life, where I get 3, 7.2 divided by 2.4 equals 3. Then I multiplied it by 1/2 and I get 0.125, where it's the amount remaining after 3 half-lives. So I multiplied 100 grams to 0.125 and I get 12.5 grams. Here's our answer. Next is Palladium 100 has a half-life of 3.6 days. If one had 6.02 times 10 raised to 23 atoms at the start, how many atoms will be present after 20 days? So here I substitute it into our formula. Then 6.02 times 10 raised to 23 multiplied by 1/2 raised to 20 over 3.6. So I get 1.28 times 10 is 20 atoms remaining after 20 days. You can use your calculator to check if it's right. Next is osmium 182 has a half-life of 21.5 hours. How many grams of a 10.0 gram sample will have decayed after exactly 3 half-lives? Note that the length of the half-life played no role in this calculation. In addition, note that the question asks for the amount that decayed, not the amount that remaining. So it's the solution. 10.0 times 1.3 raised to 3 because in the question we're given that how many grams would be left after 3 half-lives. So we get 1.25, then 10.0 minus 125, then I get 8.75 grams. So here's the answer. 8.75 grams have decayed after 3 half-lives. Next, uranium-238 has a half-life of 4.46 times 10 raised to 9 years. How much U-38 should be present in a sample 2.5 times 10 raised to 9 years old if 2.00 grams was present initially? So just direct substitute it into our formula, then we get 1.36 grams. Thank you guys. We get
Our next topic is nuclear shielding. The shielding effect describes the attraction between an electron and the nucleus in any atom with more than one electron shell. Shielding effect can be defined as a reduction in the effective nuclear charge on the electron cloud.
The size of the shielding effect is difficult to calculate precisely due to the effects from quantum mechanics. As an approximation, we can estimate the effective nuclear charge on each electron by the following. Where Z is the number of protons in the nucleus and X is the average number of the electrons between the nucleus and the electron in question. X can be found by using equation chemistry and the Schrödinger equation by using Slater's empirical formulas.
In Slater's rule, there are 3 steps. First, write the electron configuration. Second, rearrange the n from lowest to highest and then group S and P. Then everything else is separate. Third is figure which electron are you calculating for. The rules are, for the shells D or F, the sum will be 0.35 for each electron in the same group and 1 for each electron in the lower group. For the shells S or P, the sum will be 0.35 for each electron in the same group, 0.85 for the one shell lower, and 1.00 for the electron with 2 and above shells lower. An example. Find the effective nuclear charge for a 3D electron in Fe or iron. Iron is element number 26. So the first step is write the electron configuration, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. Step 2. Rearrange from lowest to highest n. So the 4s2 and the 3d6 will interchange, but that is only for the purpose of Slater's rule. And then group S and P, and everything else is separate, as you can see in the example. And then apply the rules in sum for each electron. Since we're searching for the effective nuclear charge of the 3D shell, we deduct its electron by 1 and multiply it by 0.35. Other electrons are multiplied by 1. After that, add it all up, and then the sum of these calculations will be subtracted by the total electrons of the element. The answer will be the effective nuclear charge of the given, which is the iron.